We present Dexterous world models. Recent progress in 3D reconstruction has made it much easier to create realistic digital twins of everyday indoor environments. However, a static scene alone is not enough for embodied interaction. In the real world, humans move through the scene and manipulate objects. These actions change the state of the environment. The question we ask is, can we simulate scene dynamics caused by these embodied actions inside a static 3D scene? In this work, we focus on the egocentric setting. We predict what the person would actually see while interacting with the world. On the left, we have an embodied action in a static 3D scene. On the right, we have the corresponding egocentric observation. Dexterous World Models, or DWM, takes the static scene and the embodied hand action as input. It then generates an egocentric simulation of the resulting interaction. The key idea is that the model should preserve the static parts of the scene, while generating only the dynamic changes caused by the action. Here are some other outputs of DWM in different scenes. We start from an embodied action in a 3D scene. This action contains the person's motion through the scene, as well as the hand movement used for interaction. From this action, we extract two trajectories. The first is the camera trajectory, which represents the egocentric viewpoint over time. The second is the hand trajectory, which describes the motion and pose of the hands during manipulation. Using the camera and hand trajectory, we render the action from the egocentric viewpoint. This gives us an egocentric embodied action sequence. It provides the model with spatially aligned information about where the hands are, how they move, and which part of the scene they interact with. We further decompose the egocentric action into two conditioning videos. The first is a static scene video. It is rendered along the same camera trajectory, but without any interaction dynamics. The second is a hand mesh video. It shows the egocentric hand motion that drives the interaction. Together, these two inputs separate navigation from manipulation. We implement DWM as a scene action conditioned video diffusion model. The model receives random noise, the static scene video, and the hand mesh video. Conditioned on these inputs, it generates an egocentric simulation that shows the expected scene dynamics. During training, we supervise the generated simulation with the ground truth interaction video. The ground truth video teaches the model what dynamic changes should occur as a result of that action. To train this model, we need paired data. Each training sample should include an interaction video, a corresponding static scene video, and a hand video, all aligned in time and viewpoint. We construct a hybrid dataset using two sources, synthetic human scene interaction videos, and fixed camera real-world human-object interaction videos. The synthetic data gives accurate alignment while the real-world data gives more realistic object dynamics. First, we focus on the synthetic paired dataset. For the interaction video, we enable object dynamics. The person acts in the scene, and objects respond to the action. This produces the target video, where both camera motion and interaction-induced scene changes are visible. To construct the static scene video, we replay the same camera trajectory, but freeze the object dynamics. This gives us a video with the same egocentric camera motion and the same background scene, but without the action-induced changes. We also render the hand video separately. The result is an aligned triplet. Because all three are rendered under the same trajectory, the supervision is precisely aligned. Next, we incorporate real-world interaction videos. Synthetic data is well aligned, but it cannot fully capture real physical effects, such as complex object motion, fluids, material deformation, or natural appearance variation. Real-world videos help the model learn these richer dynamics. We use fixed-camera real-world human-object interaction videos. In this setting, the camera does not move during the interaction. This fixed viewpoint makes it possible to construct an aligned static scene video without requiring a full 3D reconstruction. For each fixed-camera interaction video, we extract the first frame. Before the interaction starts, this frame represents the initial static state of the scene. We then copy this first frame over the entire video length. This creates a static scene video that has the same viewpoint and duration as the interaction video. Because the camera is fixed, this repeated first frame remains aligned throughout the sequence. This gives us the real-world pair, the original interaction video and the constructed static scene video. Together with the hand motion estimated from the video, we use these samples to train DWM on realistic interaction dynamics. A key design choice is how we initialize the model. DWM should preserve the static parts of the scene, and only generate the residual dynamics caused by the action. To encourage this behavior, we start from a video in painting diffusion model. A video in painting model already learns to preserve visible context while generating missing regions. When the mask indicates that the full video is known, the model behaves as an identity mapping, while still retaining a strong generative prior. We initialize DWM from this model, so the static scene video becomes a strong base for preserving appearance and camera motion. As we add the hand video condition and train the model, it learns to model the residual visual changes induced by the hand action. This lets DWM focus on generating interaction dynamics, instead of reconstructing the entire scene from scratch. First, we show a synthetic scene with a dynamic egocentric camera. The left side shows the static scene and hand action input. The right side shows the egocentric simulation generated by DWM. The model preserves the camera motion and scene geometry, while producing the action-induced changes. Here we compare DWM with baseline video editing or in painting approaches where DWM generates a more plausible action condition simulation. Next, we evaluate on real-world videos with a static camera. On the right, DWM generates the interaction result, including realistic object motion in the scene. DWM similarly generates a more plausible simulations compared to baselines. For evaluation on real-world scenes with a dynamic camera, we construct a dataset under a special protocol. We first capture the environment using ARIA glasses before the interaction. This capture is later used to reconstruct the static 3D scene. We also record the actual interaction with ARIA glasses. This gives us the ground truth egocentric interaction video with real camera motion. From the pre-action capture, we reconstruct the static scene using Gaussian splatting. This gives us a 3D representation of the environment before any interaction occurs. We then render the reconstructed 3D scene along the camera trajectory recorded during the action. This produces a static scene video with the same viewpoint motion as the ground truth interaction video, but without dynamic object changes. Finally, we combine 3 videos for evaluation. This gives us a real-world dynamic camera benchmark for DWM. Here is another example of the evaluation set. This slide shows multiple examples from the real-world dynamic camera evaluation dataset. The dataset covers different rooms, camera trajectories, and interaction targets. This setting is important because it evaluates whether DWM can generalize beyond its training data, from synthetic scenes and fixed camera real-world videos to dynamic egocentric real-world interactions. Now we show DWM outputs on a real-world scene with a dynamic camera. DWM successfully simulates plausible interaction dynamics in the real world with moving viewpoints. The generated simulation follows the input hand action and produces the corresponding scene change. This demonstrates the generalization of DWM to real-world dynamic viewpoint scenes. Here we demonstrate additional examples. DWM can also model some real-world dynamics that are difficult to learn only from simulated data. The output video shows an example of fluid dynamics. This example focuses on non-rigid deformation. The hand interacts with a soft object, and the generated output reflects a deformation-like visual change. Beyond video generation, DWM can be used for action evaluation. Given a static scene and several candidate hand actions, we simulate the outcome of each action using DWM. Then we compare the predicted outcomes to a goal, which can be specified either as text or as an image. Here are 4 candidate hand actions for the same static scene. Each candidate represents a different possible action trajectory. Instead of executing these actions in the real world, we first simulate their consequences with DWM. Each rollout shows what the model predicts would happen if that action were performed in the scene. These simulated outcomes can then be ranked according to the task goal. For a text-based goal, such as, "I close the microwave," we compare each generated rollout to the text instruction. We use a video language similarity score to measure alignment between the generated video and the goal. The candidate with the highest score is selected as the best action. We can also evaluate actions using an image-based goal. In this case, we compare the final visual outcome of each rollout to the goal image. The candidate with the lowest perceptual distance is selected. This shows how DWM can support goal-driven action selection through visual simulation. Thank you for listening.